Signals and Systems DT Fourier Transforms Part 3 Series on Signals and Systems Lecture number 5.13 DTFT stands for Discrete Time Fourier Transform. It is counterpart of Ctft in discrete time domain. It converts discrete time sequences into continuous frequency signals. Essentially, they are meant for showing frequency content in a discrete time sequence. In the present session, the focus is on transforms, discrete time Fourier transforms of certain standard or common signals like impulse function, step function, sinusoidal functions, and so on and so forth. We start the session with a recollection of the definition of DTFT along with certain important aspects of DTFTs. Now, let us move further to begin the core session. A few points, important points, significant points pertaining to DTFTs. In signal processing, the DTFT is a form of Fourier analysis that is applicable to a sequence of values representing discrete time signal. And this sequence may be samples of a continuous function. Whereas the CTFT stands for continuous time Fourier transform. CTFT is evaluated on the Laplace S-domain's imaginary line. The DTFT is evaluated over the unit circle of the S-domain. This is an important aspect one has to keep in mind. S-domain's imaginary line. S stands for complex frequency. It is equal to sigma plus j omega. A plane in which horizontal axis denotes sigma values, vertical axis denotes j omega. This plane is called S-plane. CTFT is evaluated on S-domain's imaginary line. Imaginary line means vertical axis. Vertical axis denotes frequency, real frequency. The transform variable in case of CTFT is omega, real frequency. The DTFT is evaluated over the unit circle of the Z domain. Z stands for R e power j omega. Different Z values can also be denoted over a complex plane. When R is 1, values of Z fall on a circle whose radius is 1. It is called a unit circle. The DTFT is evaluated over the unit circle of the Z domain. The S domain's left half plane maps into complex unit circle. There is a relation between S plane and Z plane. S and Z both are complex quantities. Both denote complex frequency. Both are transform variables. Of course, S is transform variable of Laplace transform, whereas Z is transform variable of Z transform. One works on continuous time signals, whereas the other one works on discrete time sequences. Even though this difference is there, there is underlying unity of the basic principle, basic idea between S and Z planes. S domain's left half plane, this one, it maps into complex unit circle, this one, and Z domain's outside of unit circle corresponds to right half of the plane. Right half of the plane corresponds to outside unit circle. Here one aspect to be mentioned, required to be mentioned, is that there exists some correspondence between Ctft and DTFT. Similarly, there exists correspondence between Laplace transform and Z transform. There also exists relation between Ctft and Laplace transform, a relation between DTFT and Z transform. Relation between Ctft and DTFT, it is given in the second point, whereas relation between S domain and Z domain, it is given in the third point. One way of designing digital filters is to take analog designs and subject them to a bilinear transformation, which maps them from S domain to Z domain. It is bilinear transformation that plays an important role in the design of digital filters. Then the digital filter is produced by inspection, manipulation, or numerical approximation. Such methods tend not to be accurate except in the vicinity of complex unity at low frequencies. So these are some important points pertaining to DTFTs, their relation with CTFTs and Z transforms. Now we consider the definition of DTFT. DTFT of a sequence x of n. It is usually indicated by x of omega. By definition, it is equal to sigma n equal to minus infinity to plus infinity x of n e power minus j omega n. Inverse DTFT gives x of n from x of omega. X of n is equal to 1 by 2 pi integral 2 pi x of omega e power j omega n d omega. Omega is angular frequency. Notice x of omega is continuous frequency function or signal, whereas x of n, it is discrete time sequence. Some points regarding the definition of DTFT. Notice that DTFT itself is a continuous function of frequency, which is already mentioned, and its discrete samples can be readily calculated with the discrete Fourier transform DFT. It is to be mentioned here DTFT, DFT. They are not same. DTFT stands for discrete time Fourier transform, whereas DFT stands for discrete Fourier transform. There is a connection between them. What is that connection? The discrete samples of DTFT, they can be readily calculated with DFT. Both the transforms are invertible. Invertible means we can get the original signal back from the transformed signal. The inverse DTFT is the original sampled data sequence. That's why DTFT is invertible. DFT is also invertible. Both the transforms means DTFT and DFT. We can get original signal by applying inverse transform. The inverse DFT is a periodic summation of original sequence. The fast Fourier transform FFT, it is an algorithm for computing one cycle of DFT, and its inverse produces one cycle of inverse DFT. So DTFT is associated with the DFT and also FFT. We need to have a clear cut idea regarding the distinction between these three terms or transforms. Now we move to the core topic of this session. We consider to find the DTFTs of certain standard or common signals. We begin the session with signal delta of n, impulse function, Kronecker delta function. It can be seen its DTFT is equal to 1. How to get this result? Apply definition of DTFT both sides. DTFT of delta of n is equal to sigma n equal to minus infinity to plus infinity delta of n e power minus j omega n. It is equal to 1. Next signal, shifted delta impulse. DTFT of delta of n minus n naught can be seen as equal to e power minus j omega n naught. Again using the definition, DTFT of delta of n minus n naught is equal to sigma n equal to minus infinity to plus infinity delta of n minus n naught multiplied by e power minus j omega n. Now we make the substitution n minus n naught by k. It results in transform of x of n minus n naught equal to sigma k equal to minus infinity to plus infinity delta of k e power minus j omega k plus n naught equal to e power minus j omega n naught sigma k equal to minus infinity to plus infinity delta of k e power minus j omega k, which is e power minus j omega n naught delta of omega, which is of course e power minus j omega n naught. Hence, delta n minus n naught, its Fourier transform is equal to e power minus j omega n naught. Another transform, we consider the transform of 1. It can be seen it is equal to 2 pi multiplied by delta of omega. Here, in understanding this relation, connection, transform, we use the inverse transform defining relation. X of n is equal to 1 by 2 pi integral 2 pi x of omega e power j omega n d omega. Now make a substitution 2 pi delta of omega for x of omega. So x of n becomes equal to integral 2 pi delta of omega e power j omega n d omega, which turns out to be 1. Here we have used the sampling property of impulse function. Another signal e power j omega naught n. For this, DTFT is equal to 2 pi delta omega minus omega naught with x of omega equal to 2 pi delta omega minus omega naught, x of n equal to integral 2 pi delta omega minus omega naught e power j omega n d omega. It is equal to e power j omega n naught. Here also we have used the defining relation of inverse DTFT. Another signal cos omega naught n sequence. Its DTFT can be shown equal to pi times delta omega plus omega naught plus delta omega minus omega naught. How the process is given here. Transform of cos of omega naught n is equal to sigma n equal to minus infinity to plus infinity cos of omega naught n e power minus j omega n. Now cos can be replaced by exponential functions, and it is done here, resulting in sigma n equal to minus infinity to plus infinity e power j omega naught n plus e power minus j omega naught by 2 e power minus j omega n. After a little bit of manipulation, one can see that it is equal to transform of e power j omega naught n by 2 plus transform of e power minus j omega naught n by 2. Of course, then it becomes equal to pi times delta omega plus omega naught plus delta omega minus omega naught. Hence the relation. By following a procedure similar to the procedure which we followed in finding the transform of cos omega naught n, one can determine DTFT of sine omega naught n as j pi delta omega plus omega naught minus delta omega minus omega naught. Now another signal unit step sequence. DTFT of unit step sequence can be shown as pi delta of omega plus 1 by 1 minus e power minus j omega. Using the accumulation property of DTFT is DTFT of sigma minus infinity to n x of k, it is equal to pi x of 0 delta of omega plus 1 by 1 minus e power minus j omega x of omega. And this is accumulation property. And the fact that u of n is equal to unit step sequence, it is equal to sigma minus infinity to n delta of k. So this is the connecting relation between step sequence and delta function. Using accumulation property and the connecting relation between step and delta, one can simply write down DTFT of u of n as pi delta of omega plus 1 by 1 minus e power minus j omega. Similar way, by following similar procedure method, it can also be found that DTFT of minus u of minus n minus 1, it is equal to minus pi delta of omega plus 1 by 1 minus e power minus j omega. Another signal sequence, we encounter this sequence frequently. A power n u of n, its transform can be shown equal to 1 by 1 minus a e power minus j omega. To find this relation, apply DTFT definition to the signal. Transform of a power n u of n is equal to sigma n minus infinity to plus infinity a power n u of n e power minus j omega n equal to sigma n 0 to infinity a power n e power minus j omega n. So it simply becomes equal to 1 by 1 minus a e power minus j omega. Another sequence, minus a power n u of minus n minus 1. Its transform can be found equal to 1 by 1 minus a e power minus j omega. Now, using the definition of transform of minus a power n u of minus n minus 1 becomes equal to sigma n minus infinity to plus infinity minus a power n u of minus n minus 1 e power minus j omega n. A little bit of simplification and manipulation leads us to give it equal to 1 by 1 minus a e power minus j omega. With this, we come to an end of this session. Before closing down, let us recollect the important points that are touched in the present session. After giving a brief on definition of DTFT, we entered to find transforms of various standard common signals like Kronecker delta, step, sine, cos, so on so forth. Hope this session is useful to you. We meet again with a new topic in another session soon.